So we are very happy for the next talk to announce Elli Pomoni, who actually started her career with, among other things, with integrability. And then in the meantime, she has done many exciting things, but I'm very happy to see that you also still work on integrability and tell us something new today, right? Or
yes.
Yeah, wonderful.
Thank you, Matthias. And let me begin by thanking the organizers for having me here. It's great to give a talk again in person. So this stuff, I started in my PhD, and we were asking if the spin chain of n equal to 2 superconformal theories are integrable. And in fact, in one of the IGST conferences many years ago, I was bugging Kostas Zoubos, and I was asking him, because he knew back then how to do Q deformations, if we can maybe do something. So, you know, IGST was very important to start new collaborations, yes? So, and this is work with Randl Rabbe. Okay, I want to do this, I'm sorry. He graduated now, but we have other amazing PhD students. Enrico has a poster outside. You can go and ask him questions. And Hano, he's my PhD student from DESI, and Sinyu is a postdoc at DESI. Okay, so first of all, we stick to 4 dimensions. I'm sorry if your favorite number of dimensions is 3 or some other number. And well, n equal to 4 is integrable. This is what this conference is all about. And the question is, can we go beyond that in a nice, organized way? And okay, I have my little star here. If this is the only integrable theory, we know that it's not, but it's very sparse, the theories. We know that they are integrable. And again, I want to be able to, step by step, remove supersymmetry and see what will happen to me. And I hope I can convince you that we can do this in an organized way by the end of the talk. So first of all, in the past, and maybe there are still people here in the audience that believe that, people believed that the moment you go down to n equal to 2 even, integrability is gone. And why is that? It's my fault. We wrote this paper back in my PhD years. And we checked the Young-Baxter equation, and we found that it's not satisfied. And back then already, we said that it's not integrable when we all got depressed. And nobody complained about that. Nobody complained in all of these years. But we can complain to ourselves. So let's, like in a very basic way, when we think about integrable models, how we should think. So there are rational integrable models, like the XXX spin chain, right? And this has SU2 symmetry. And the moment you break a little bit by introducing a little bit of homogeneity, you get to XXZ, and you have a trigonometric model. And already there, you can find the quantum groups playing a role. But the moment you really break isotropy completely, naively you think there is no symmetry in the problem. But then, if you think again a little bit harder, you discover that there are elliptic quantum groups that govern what is going on. And in fact, there is even more than that, and there are many crazy papers that do this. There are hyperelliptic models. And in fact, if you really want to go all the way to study generic n equal to 2 and n equal to 1 theories, these will come up. Now, I want to argue why the Young-Baxter equation argument was just wrong. First of all, when you have an elliptic model, it really very much depends on the basis on which you decide to describe your model. So that if the Young-Baxter equation is the criterion or not, or something else, the dynamical Young-Baxter equation of Felder is the actual criterion. And for the people in this audience that the word dynamical takes them to Bizert, so this is not the same dynamical thing here. Now, the basis in which the elliptic model satisfies the Young-Baxter equation, we could think of it, we could call it Baxter. It's the Baxter-Bellavin R matrix that does that. But in that basis, we have Sklianin algebra acting on our states. And the moment you have Sklianin algebra, there is no highest weight states. But we are studying superconformal field theories, and superconformal field theories have BPS operators. And BPS operators, when you map them to the spin chain states, are highest weight states. So it's simply wrong to think that you are in these bases. So it's simply wrong to think that the Young-Baxter equation is a criterion. Is everybody happy with this? So this is where we start from. So this argument was just too naive. And this is the correct way to think now. Fantastic. Now, mathematicians, of course, know more than us. And there are much richer structures than elliptic models. And in fact, already from Drinfeld, we know that the moment you have a Drinfeld twist, you can construct beautiful Quasi-Hopf algebras. And they come with even more advanced Quasi-Hopf Young-Baxter equations. And here is how it looks. So there is a lot to play with. And I will try to show you that this is what we have. And then if you want to ask the question of integrability, the way to do it is you ask if your Drinfeld twist obeys a certain cocycle condition. And if it does, your model drops down to a dynamical Young-Baxter equation, and it's integrable in the elliptic way. Yes? And by the way, if your model is hyperelliptic, we don't even know what is the criterion. But one should do this derivation again from scratch. So this is a little bit to set the scene where we are. Now, OK, n equal to 4 super Young Mills, the moment you say, I want to do SUN, the theory is unique, you have a coupling constant, that's it. But for n equal to 2 theories, even for the superconformal ones, there is a landscape of theories as long as you want a Lagrangian description, but they are classified, and the classification is in this paper. And for most of them, the way to obtain them, and this is like as an exercise in our mind, this is really the best way to think. You should always think that we take n equal to 4, an orbifold, and then you marginally deform with all the possible marginal deformations. And this is the way to create most of the landscape of n equal to 2 theories. Yes, and this is a fantastic organized way to go for it. And because of that, because of the orbifolding procedure, we actually know what the gravity duals of these theories are, so we can also do a SCFT. And we also know that at the orbifold point, so when these coupling constants are all equal to each other, we also know that these theories are integrable. So the only thing we need to learn how to do is we need to understand what marginal deformations do. That's the only thing we need to understand. So here is the main example. So if you are an n equal to 4 super Young Mills person, it would be nice. If I had a blackboard, I would transfer some of these things on a corner so that we cannot forget them. But it would be nice to try to remember a little bit from this slide. So the main toy model here is an SUN cross SUN gauge theory. So here are the two color groups. They have fields in the adjoint representation. These are scalars. And there are also fields that are bifundamental. And the way you get them when you orbifold is you originally think that you have x, y, z. These are the n equal to 4, 3 scalars. And after the orbifold projection, some of their elements go to 0, and that's how you get the bifundamental or the adjoint matter. Yes? And when this is G1 and G2, the coupling constant of these color groups, when they are equal, this is when we have the orbifold point. So this theory is enough to study and discover, first of all, something that I will try to show you in the coming slides, that the spin chains of these theories, the correct way to think of them is that they are dynamical. And from that, elliptic or hyperelliptic, all of the other things come. And another thing that maybe many people ask, so I just say it from now, so we are done with it. If you want to study super QCD in the Venetiano limit, you should first understand this theory and then take the limit of one of the two couplings to go to 0, and then you win. That's the only organized way to really succeed in playing this game. And if you don't believe me, you can ask me afterwards why this is the case. OK, so now we go to the technical stuff. Let me summarize what I will do. First, I will talk to you a little bit about one-loop spin chains, because it's very important that we organize our mind for how to think about the Hilbert space. And I will try to show you in a very basic way why they are dynamical. And then I will concentrate on the quantum symmetries. So the main thing for this talk is that I want to show you that we have a Quasi-Hopf symmetry algebra. I want to show you that it's very easy to read off the R matrix in the quantum plane limit and get the twist, the Drinfeld twist. And then once we have that, we basically need to understand it. And we will have a coproduct with which we act. And then we can see how our spectrum then gets organized in multiplets of this quantum group. So this is the plan. Are there questions? Okay, then let's go. So first of all, one-loop dynamical spin chains. First, let's start with something very easy. And this is this xy sector. X and y are the two scalars that after the orbifold projection, they are bifundamentals. And because of that, most of the people in the audience should like this sector very much because it looks very much like ABJM. So it is actually an alternating spin chain. And the good way to think about it in the dynamical language is you start from an n equal to 4 state. I think that I take the trace and I cut it open and I have an open state, yes? And the moment I do that, the only thing I need to do extra to specify which one of my states is my n equal to 2 state, I only need to specify for you the first open gauge group. And the moment I do that, the rest is dynamically specified by following the color indices. There is nothing else I need to do. So no, at this stage, I will always cut and open my chain and study open chains. And only in the very end, I will glue things back. I mean, this is also how we do most of the things for n equal to 4, so let's also do it here. And here is my little Chan-Paton label that tells me what is the first open index. So all n equal to 2 states can be labeled in this dynamical way of thinking. Yes? So this is an alternating spin chain, and actually this is maybe in some ways too much notation. But the moment you do that, you already start seeing nice things happening to you. And one nice thing is that okay, back in the day, we were writing the Hamiltonians in this way, and this is the Hilbert space. But now when you go to the new dynamical language, here is the new dynamical language, you can see with your bare eyes that in fact what you have is an XXX Hamiltonian, but you have it with a different coefficient depending on which of the two dynamical states you act. Yes? Here there is this 1 over kappa. By the way, kappa is the ratio of the coupling constants, and here is with kappa. So what do we have? We have a dynamical XXX spin chain. And the way these two XXX spin chains couple is dynamically determined by the basis, by the Hilbert space. Let's now do something a little bit harder. So let's involve fields that are in the adjoint representation. Then we cannot be alternating anymore. It's more interesting. And the moment you have these z's going twice, the fields in the adjoint, you can... Sorry, loud. So if they are two different sectors the way they are different sectors for n equal to 4 super Young Mills. I choose my R symmetry. So yeah, this is a little bit the problem. I want you to try to remember this slide. So when I write phi 1 and phi 2 or z, these are in the adjoint representation. And this index tells me that this is adjoint in the first color group, adjoint in the second color group. Here, these gadgets, they have two indices, 1, 2. And this means that this is a bifundamental guy that starts from here and goes here. If I have 2, 1, it goes back. That's the notation. Good. Here. So again, a little bit harder, but still the same principle. What is the principle? I take the n equal to 4 state, I cut it open, I specify the first color group, and these are my two n equal to 2 states. And here is how we do it in a dynamical language. We just specify the first open color index. That's it. And then we go and we look at the Hamiltonian again, and we write everything beautifully in the dynamical notation. And what do we see? We see this is the temporally Lib Hamiltonian. And you know, the one from the other, the only thing that they differ is that this kappa goes to 1 over kappa. So we have a dynamical temporally Lib Hamiltonian. That's what we have. Yes. Dynamical refers to the color index, if you wish. Yes. How So the Hamiltonian always is defined on which, let's look at here, which element specifically of the Hilbert space it acts. They do speak to each other, because if this is Q12 and this is Q21, when you have Q21 and you want to act to the next guy, you move to this. So they do speak. So your chain is not only two things, it's many things. And if this is the first and the second guy, then this can be the second and the third, and so on. So they do very much speak to each other. Yes? If the Hamiltonian was the one for the y sector, what you say is perfect. If we go to this sector, where you have the z's, and they can be as many as you like, you lose this ability to do that, and it's truly a dynamical, full-on dynamical. And we have to live with that. I mean, okay, the truth is that now I could start a whole talk that I am not going to do, how this goes all the way to Felder-like models. And to maybe to some people's disappointment, I won't do that because I want to talk more about the quantum groups. But let me say some words about that. And this is, all of that is in this paper. So first of all, this is a very old idea. So this looks like you have trigonometric models that somehow you put them together, you know, a trigonometric model with the formation parameter kappa, a trigonometric model with the formation parameter 1 over kappa, and somehow you put them together. And in fact, not even here, this goes back to Fatev and to Takhtajan, like Leningrad Integrability school, that you can make elliptic model by averaging trigonometric models. But a very beautiful way to think, especially now that I have introduced this 1 and 2, is to go to Felder and think that his dynamical parameter, in fact, does precisely that, keeps track of the color group. Of course, this is not quite Felder because of this adjoint field. And what this adjoint field does, it doesn't change the dynamical parameter. So what we actually have is a restricted solid-on-solid, or better, cyclic solid-on-solid model. And I will just say that this is a result that I will not explain at this stage. If you want to study the holomorphic SU3 sector of these chains, we have explained in this paper that this is captured by a dynamical 15-vertex model. And this is a very beautiful story to study in the future. Okay, but I continue. Okay, now let's go to the symmetries. Because if you want to understand integrability, better first to understand the symmetries of the problem, right? So, first of all, how are we going to discover these Quasi-Hopf symmetries? First, I give a quick summary, and then I go into it and I explain. The way you discover it is basically the same way people discovered how to study marginal deformations of n equal to 4 super Young-Mills. And what you do is you begin by looking at the F terms, or the superpotential of the theory. And the moment you have these define complex quantum planes. And by having the quantum planes, you immediately can write down the R matrix. The R matrix in my baby language is basically the moment you plug in the matrix in this eigenvalue equation, you get the quantum plane back. And this is enough to check that superpotential is invariant under quantum group and all the other things that I will do with the BPS states. So let's start doing it, and let's start with the most baby example possible. So let's take two coordinates, x and y. This is the famous Manin quantum plane. And okay, we open a quantum book and we copy the R matrix and we plug it in here and we say, okay, this is how I get my quantum plane back. But what is very interesting is that now we can discover the symmetry transformations of this quantum plane. And here are the symmetry transformations. When I put x1, I mean x, and when I put x2, I mean y, right? So how do I get the quantum group? I just take my R matrix and I plug it famously in the RTT equations, and I get the algebra. That's how we do it. So let's now go to what we need. So what we need is we need three-dimensional complex quantum planes. And these are classified mathematicians. And the mathematicians tell you that if you want to do that, you need to know two tensors, this E and F, with three indices. And the moment you know these two tensors, these define the quantum plane and the quantum coplane. And the moment you have them, you can plug them in these equations. C is just a constant, and you have your R matrix. And this is the R matrix that when you plug it in the RTT, it gives you the quantum group. That's how we are going to do it. First of all, before I say how we will do it, let me remind you that this is how it was done for the marginal deformations of n equal to 4 super Young-Mills. So either you write down the F terms, which define the 3D quantum planes, or you just look at the superpotential of n equal to 4 super Young-Mills, you write down the List-Lassler, and you ask, what do I need to replace the Levi-Civita simple with which tensor? And this is the E and the F that the mathematicians need in order for us to write down our R matrix. And you can write down the R matrix, the Hamiltonian, everything, and you discover there is a quantum version of SU3 that leaves this Lagrangian invariant. Now, before we go to the theory, I want to say one more thing. We understand this, in fact, from the SCFT also. And how do we understand it? Well, in the gravity dual, when you have a B field that is turned on the transverse 6 dimensions, what happens is that you just read Seiberg-Witten, and what they tell you is that when there is a B field and your open strings end on the D3 branes, they see a non-commutative geometry. So this non-commutative geometry is the quantum plane. So these open strings see precisely this quantum plane. And for the List-Lassler, this was done by Manuela nicely. And I mean, if you want, you can read our paper for how to do this for the orbifold. Okay, now let's really say what is this structure. So here, for the Z2 quiver theory that I showed before, here I write the F terms. They come into two chunks because it's a Z2 orbifold, so there are two images. So there is always this thing with the two images. And the way I read off my E and F tensors is that I replace the Levi-Civita of n equal to 4 with whatever is needed so that I get my correct n equal to 2 Lagrangian. And here is written what is needed. And the moment you do that, you have an R matrix. For the XY sector, this easier alternating one, you basically get the identity, which is great. And for the other two SU2 sectors, which are these more truly dynamical ones, you get a non-trivial R matrix. With the property also, if you look slightly closer, that this with this is kappa going to 1 over kappa. And the fact that the XY sector has a matrix proportional to the identity, what does it mean? It means we have an SU2. And yes, we know we have an SU2 because this is the SU2 symmetry of n equal to 2 theories. And the XZ sector, the fact that it has this non-trivial R matrix is precisely because this SU2 symmetry naively is broken. But what I'm trying to tell you is that it's not broken, it's upgraded to a quantum SU2. And okay, here is the R matrix again. You can plug it in the RTT relations, and you precisely get SU2 kappa quantum, yes? And on the top of that, by splitting the R matrix in this way, you in fact get the Drinfeld twist. So you actually have a full-on Quasi-Hopf symmetry algebra defined basically by this Drinfeld twist. So up to now, here is everything is beautiful, but it's somehow very formal, and I can say that I almost don't like it. I want to do something very concrete. So let's do something very concrete. I want to make multiplets. If we have a symmetry, we should be able to make multiplets. So the point is, let's try, we have our beautiful twist. Let's try to write down a coproduct with our beautiful twist in such a form so that we can actually act with our naively broken generators and see what happens. So the moment you do that, the moment you have such an action, you can first of all ask, is my Lagrangian invariant? Is my superpotential invariant? And the answer is yes. It is indeed invariant under an SU3 kappa deformed, precisely the one that I get by embedding these SU2s. And not only that, what we can in fact do is that we can construct, by acting with these broken, at least naively broken generators, we can construct SU2 kappa deformed and SU3 kappa deformed multiplets. And we can see, for example, that the BPS spectrum organizes into multiplets of that. And let me show you examples. So if you have ever studied a tiny little bit of n equal to 2 theories, you know that, for example, this state here, where it's like the adjoint scalar of one color group, and this state here that looks like some type of baryonic state, they live in completely different n equal to 2 superconformal multiplets. But if you act with this broken, with our new coproduct generators, you can in fact make a multiplet in which all of them live. And not only that, all the states in the middle, you can all get them by diagonalizing the Hamiltonian. And not only that, this coproduct precisely reproduces a very precise prescription for all the coefficients inside the operator, which is reproduced by diagonalizing the Hamiltonian. This is actually quite fascinating. And you can do this for SU2 multiplets, and you can also uplift it for SU3 multiplet, but I didn't want to draw an SU3 multiplet here. Another really cool thing, because you know, okay, SU3 holomorphic, at some point we had a real fit, and I was like, maybe there is something wrong. So I really wanted to embed everything to the full SU4, because then you also get non-holomorphic things. So for n equal to 4 super Yang-Mills, we have the stress energy tensor multiplet, right? And the bottom of it is the 20 prime. So here is the 20 prime in an n equal to 2 language written. And the green lines, you can see them faintly. They are SU2 generators, so they are really there and they are unbroken, and we have them. But the blue generators are all broken naively, and this is not a multiplet. However, if you use this coproduct, you can reproduce this whole multiplet. So what am I telling you? I am telling you that the n equal to 2 spectrum lives in kappa deformed n equal to 4 like multiplets. Any complaints? Sorry? So this statement, you could call it a one-loop statement. So at this stage is BPS. It will stay, yes, it will stay. But of course, what we want to do is we want to use something like this for everything, right? So what I can show in almost, yeah, okay, good. So first of all, let me make a conjecture. So my conjecture is this, that if you have a theory with less supersymmetry than n equal to 4, that you obtained by doing something like orbifolding, I think orientifolding, all of these procedures go the same way, from the mother n equal to 4 theory, it will enjoy a quantum deformed version of the PSU2, 2/4. This is my statement. And all the naively broken generators will be basically upgraded to quantum generators. And let me try to visually put it in your head. So when you have less than n equal to 4 supersymmetry, what you need to do is you look at the F terms. They are not defining anymore simple planes. They define quantum planes because they are sprinkled with all the coupling constants. And from them, we can read off their matrix the way I described, and we get what is the quantum group that acts on them. And precisely the way I described, from their matrix, we read off the Drinfeld twist, and from the Drinfeld twist, we can have everything that we ever wanted that the Quasi-Hopf symmetry algebra has. Now, first, let me say where we currently stand. So first of all, I described everything for this Z2 quiver, but we equally well can do everything for any A-type orbifold we worked out. Of course, I am pretty sure whoever wants can do a T-type orbifold or E, or I mean, it just depends on the plane you want to go through. We are currently working out more multiplets. So basically, I want to have Dolan Osborne, the whole thing. I want to have it, you know, quantum deformed now. So here is maybe for the question. So what we have now is we did states with length 2. So when you do 6 times 6 of SU4, you have 1 plus 15 plus 20 prime. 20 prime is the protected, but 15 is a guy, 15 and 1 are not protected. Okay, 1 is not quite a multiplet because it's just a singlet, but 15 defines a new quantum multiplet. And this is not protected. Yes? And then continue. Okay, I already mentioned that there is this 15 vertex model, that this is very important. Another thing that I didn't mention, which is also very important, is we have an explicit coordinate Bethe ansatz in the previous paper. And you can see immediately all the elliptic happiness coming in. This is an one loop result. When I show this to n equal to 4 people that they know this, you know, to all loop, to say that this is an one loop result is pretty amazing, I think. And of course, you can do this with the scattering matrix and everything. You really need to use theta functions to do the work there. And there is a brute force computation. I mean, Anna will show later some amazing things that they are doing with Marius. And what they are doing can be imported to study these things very nicely. This is one loop. You use the one loop dilatation operator, you act, you do the coordinate Bethe ansatz, and you get this type of square root. The ratio. So, sorry, what I am doing here is that I have, in this formula, I have G1 over G2, and as long as they are finite and between 0 and 1, I am fine. Yes? So this formula will remain. It's really weak coupling formula. No, because this is a one loop formula. I mean, I can try to derive the same formula. So with Christoph, for example, we already have a 3-loop Hamilton, you know, like. But the amazing thing is that it's already elliptic. That's my point. Yes, and where we are going, so actually with this spectroscopy that we are doing now, the moment, in fact, you study 2 sites and 3 sites, you can already formally answer the question of integrability. Of course, maybe you can say that this is a useless, but for me, it's the most important thing. I want to say yes or no. And all you need to do is, I mean, we really need to very carefully write down all of our multiplets. and then say the twist between three sides, the twist between the two sides, what is the cocycle condition? And this will answer this question. So this is happening, and this hopefully will happen soon. And then all the things we love from n equal to 4, they can go through. They can just simply go through. And also n equal to 1 theories, as long as we have a nice description that we start with D3 branes and some conifold, orbifold, singularity, something, everything goes through. And okay, this is more like a, so at some point, I mean, I don't know, I am definitely very interested, but there are experts in this audience that they are really good with the gravity side. So we really need to do something about the gravity dual and start calculating there. Yes, so please, I want to recruit people. And there are also two other very interesting things. So Francesco is somewhere there. We really need to generalize these works of the dual of free n equal to 2. We really need to see the quantum string coming up. And something very similar also should happen with the Chern-Simons approach. Yes? Bogdan, yes.
Questions?
It's not on, most probably.
Ah, all right. Okay. I wanted to understand better what you were saying about the multiplet, the 20 prime. So my understanding is that you have the multiplet, and now you can move through this arrow through some quantum group operator, which is not the usual algebra generator that you would have in PSU 2,2/4. And then I presume that when you go from one level to the other, your dimension will increase, but not by half, by something else that you can compute. Is that?
So let me say slowly what this thing is.
Okay.
So first of all, I said it, but let me say again, these arrows are generators that are truly there. They are the SU2R symmetry generators of n equal to 2. So in this direction, nobody can stop you from moving, even with the old knowledge. So this is Dolan-Osborne. The new stuff is the blue arrows. The blue arrows are the generators that are naively broken because the orbifold broke them when you came down from n equal to 4 to n equal to 2. So these were generators that existed only in the n equal to 4 theory. They are SU4 generators. Yes? And now we have this new coproduct that takes these SU4 broken generators, it sprinkles them appropriately with kappas, and it does whatever it needs to do to them. And the moment you have them, you can in fact, this is a calculation, it's not a drawing.
Yeah,
you have this operator, you act with this coproduct on it, and you get this operator.
But
you act
my
with
question
the
is,
coproduct, and you go down.
Can you compute from this action of the quantum group, can you compute the dimension of the various operators that you have in this diamond? Because
I mean,
normally
I
it's
can
very
compute,
easy, right?
what do you mean that I can compute explicitly the whole picture, like arrow?
I mean, normally I know that when I go down with one of these arrows, which would be, I guess, a supercharge, in the usual undeformed case, delta minus j increases by a half. In the deformed case, it should not increase by a half.
You can define the same thing. You can define the same thing.
I mean, my point is that normally I would expect these things to get an anomalous dimension, right?
Okay, so this is a BPS. So maybe this example is not good.
It shouldn't be because you don't have the...
Wait, good. So when this is not a BPS state, so when if...
No. This whole multiplet is no longer BPS.
Yes, so if this was not BPS, but it was, let's say, the 15...
No. In this case, you start from something that used to be BPS, but is not BPS anymore, right?
No, this is BPS.
Then I'm afraid I don't. I mean,
so
even
these
in the normal,
operators,
like beta deformation and so on, these guys
wait,
get
wait,
anomalous
maybe
dimensions,
you don't
right?
understand. Wait. So this, for example, this operator is the famous Coulomb branch operator of n equal to 2, and they form a chiral ring, and they are BPS and forever protected. These are mesons, and they are in the multiplet of the flavor current of n equal to 2 theories. So these are also known to be protected. This thickly graphic is also another protected, known to be protected, is the chiral primary of the stress energy tensor multiplet of n equal to 2 theories. So all of these gadgets are all known to be protected, and they have all the same anomalous dimension equal to 0.
I see.
So clearly, the energy of all these babies is 0, or anomalous dimension. What changes as you move is these quantum numbers here.
I see. And in the case where you started from a different guy, then I'm a bit confused because there are descendants of the vacuum in n equal 4 superior Mills that once you, let's say, turn on an orbifold or a beta deformation are not protected anymore, and they are still descendants of the vacuum.
Yes, very good. Let's
but
go slowly.
But not of the 20 prime, of longer, like 3
yes,
to
so
the j.
First of all, one very sad thing in life is that nobody worked these things out for the beta deformed. And I think I'm going to wait a couple of more months, but if nothing appears, I will just do it. So my conjecture is that you should be able to do this for the beta deformed.
I don't think so, but we can discuss it later. Maybe.
Yes,
but
I think so.
The argument is that the jump in anomalous dimension of these guys that used to be BPS but are not anymore is something very.
So I think you are confusing. I think you are confusing different things.
Okay. Okay, we can discuss
the mesons and all chiral operators, first of all, it's clearly they are going to, so also n equal to 1 theories have chiral rings. So this multiplet, apart from maybe these guys for n equal to 1 theories, are guaranteed to be protected because they will be in the chiral ring, and this guy is the stress energy tensor. So they are guaranteed by n equal to 1 representation theory to be protected.
Okay.
Burkhard?
Just on Alessandra's point, I mean, I know, for example, if you take like the length 3 or length 4, and you have the manifest in beta supersymmetry, then of course you will have these properties. But as soon as you go transverse somehow, the anomalous dimension is just going to be order beta squared, right? I mean,
sorry, wait. What do you mean when you say you go transverse?
I mean, I don't take the manifest symmetry and beta deformation, but I sort of take some other direction, which should be quantum according to you. Then you will get.
I don't understand what you want to do. Sorry.
You have n equals 1 supersymmetry,
yes.
which is manifest from the n equals 4, right? And beta deformed.
So what you need to do is you take the n equal to 4 multiplet, whichever one you like. You decompose it the way Dolan Osborne tells you into n equal to 1 multiplets. This is very easy. Naively, you think they are all broken and they should never talk to each other. But what I am trying to tell you is that if you define a coproduct in this form, if you can do this, of course, in this case, we can explicitly do this. If you can write down such a guy, then you can fill in the gaps.
All I'm saying, what I know essentially is that take a state which is like a z to the 3rd, 4th, whatever. You don't even have problems with this length 2 stuff in beta.
Yes.
And act with anything which is not the manifest symmetry. Then you will create states which have anomalous dimension that have sort of beta squared plus blah, blah, blah.
Question, do you do this for the beta deform or for the gamma deform? Because gamma deform is not supersymmetric.
Let it be beta. I mean, we were looking at
then
beta.
we should talk for precisely the way you write things down, because in our case there was a tricky point that for me it took basically a couple of months to understand how to do this guy. And what was the trick? Okay, I say it openly. So you need to change the boundary conditions of your open chain. So you can always, for example, when you compare the temporally lib with the xxz, they are not the same Hamiltonian, right? But if you want to discover as you took quantum, you need to use the temporally lib Hamiltonian. And the difference from the one to the other is different boundary conditions. that you impose on the open chain, that of course after tracing, these things are gone. Yes? So maybe this is the problem.
Well, I know that I was sort of critical about the same point when you gave the talk in our place, but a few months have elapsed, and maybe
yes,
you can...
so the few months is precisely this guy.
Please tell us.
Yes, yes.
Okay, thank you.
Yes.
Okay. Dima was first.
Actually, now I understand that I missed point when you showed why it's integrable.
Well, I didn't say why it is integrable. I said that this is not in this talk. In this talk, I only want to understand the quantum symmetry. And the only way to find the final answer, I don't have it yet, the final answer is here. So the moment these things are done, completely perfect, then you ask this question. When you have the twist for 2 sides, 3 sides, you write out explicitly the cocycle condition that takes you from 2 to 3, and depending on how it looks like, it can be integrable, yes or no. What it is definitely is it is Quasi-Hopf. For maybe I show here. I had it at the very beginning.
No, maybe I can clarify slightly. So for n equal 4 super-Young mills, integrability not super conformal, but it's Youngian. For one loop.
So now it will be a quantum elliptic.
So you showed for the moment only deformation of superconformal algebra, but Youngian version of
no, I don't have it. Yes.
But do you was it somewhere hint when what you should check? Maybe I didn't.
No, nothing is hidden. In order to really show which precisely quantum toroidal algebra this is, you need to first understand this.
Okay.
So this is not done yet. Okay. This is coming.
Okay, there was one more question here. Maybe the last question, actually.
Thanks for the nice talk. I was wondering if you had a 3-point function, let's say, which involved epsilon.
3-point function I don't have.
3-point function with some with epsilon 2, and you wanted to compute the 3-point function with d in this super multiplet. Can you use this operator that goes from...
You want to do bootstrap now?
I'm just wondering, does this operator that goes from epsilon 2 to d2 allow you to compute?
Yes, so you want to do bootstrap, so amazing. So once this is done and we believe it, we need to basically take what you are doing and define the quantum blocks of the quantum PSU 2,2/4, and then we can do bootstrap for that.
But okay, I'm asking maybe a more basic question. Like if I had n equals to 4 supersymmetry, I would only have one OP coefficient for this whole diagram. And here, would it be some integral transform that takes me from the 3-point function involving epsilon to the 3-point function involving d, or? But
you need to know the OPE, right? You need to do something with this. So, nobody knows anything. It's the first time anyone says these words now. So we need to take these words and make them everything else that we know for n equal to 4. We don't know. So up to now in our life, we either do n equal to 4 super Young mills and we use the n equal to 4 super conformal algebra, or we do n equal to 2 and we use the n equal to 2 super conformal algebra. What I am saying, we have to do everything from scratch again.
Thanks.
Okay, I think I see no more questions. So let us reconvene at 5 o'clock. So we have a nice break, but let us thank Elli one more time.